In this video, I'm going to show you how to build a smooth and responsive main camera like this. First, we create a new C# script called player camera and attach it to our main camera. Inside the script, we start by defining a transform called target. This will be the player that the camera follows. Then we add a vector tree called offset. This controls the distance and position of the camera relative to the player. For example, slightly above and behind. Finally, we define a float called smooth speed. This will control how smoothly the camera follows the target. In this part of the script, we are inside the late update method. Late update is called after all other update functions, which makes it a good place to handle camera movement. The first line checks if the target exists. If the target is missing, the method stops immediately. This prevents errors in case the player object is not assigned. Next, we calculate the desired position of the camera by taking the target's position and adding the offset. This gives us a point behind and above the player. Then we use vector tree. Lerp to smoothly move the camera from its current position to the desired one. Lerp creates a gradual transition, which makes the camera movement feel more natural. Finally, the camera rotates to look at the target. This ensures that no matter where the camera moves, it always keeps the player centered on the screen. Now let's create a new empty game object and name it target. Make it a child of the player, so it follows the character automatically. Then go to the main camera, find the script component, and assign this target object to the target field. Now we add three variables that will control how the camera rotates based on mouse movement. The first one, mouse sensitivity, lets us adjust how fast the camera reacts when the player moves the mouse. Then we create two variables called yaw and pitch. These will store the horizontal and vertical rotation of the camera. Here we lock the mouse cursor to the center of the screen and make it invisible. This is important for a third-person camera, because it lets the player move the mouse freely to rotate the view without the cursor leaving the game window. Now we can delete the code we previously wrote inside late update, right after the check for the target. From this point on, we will keep late update clean and organized by splitting the camera logic into separate functions. This makes the script easier to read, easier to debug, and much more beginner-friendly. The first function we add is called handle input. Its job is to read the mouse movement every frame. Here we use Unity's input system to get the horizontal and vertical mouse values. We multiply them by our mouse sensitivity and by delta time to keep the movement smooth and consistent. Then we update the yaw and pitch variables. Yaw controls the horizontal rotation, while pitch controls the vertical rotation. We subtract the mouse Y value to get a more natural camera feeling. This function will later be used to rotate the camera around the player in a smooth and responsive way. Now let's take a look at the function that actually moves the camera around the player. The first thing we do here is create a rotation using the current pitch and yaw values. These two variables come from the mouse input we handled earlier. By converting them into a quaternion, we can rotate the camera smoothly in three-dimensional space. Next, we apply this rotation to the offset. The offset represents the camera's position relative to the player before any rotation is applied. When we multiply the rotation by the offset, we get a new vector that places the camera behind and above the player, but now correctly rotated based on where the player is looking. After that, we calculate the desired position of the camera by adding this rotated offset to the player's position. This gives us the exact point in space where the camera should move. Then we use vector tree, lerp to smoothly transition the camera from its current position to the desired one. Lerp blends between two positions over time, which removes any sudden jumps and makes the camera movement feel soft and natural. Finally, we call lookat on the camera, pointing it directly at the player. This ensures that no matter where the camera moves, it always keeps the player centered in the view. Once this function is ready, we can go back to our late update method and simply call move camera from there. This keeps late update clean and makes the script easier to understand, because each part of the camera logic is now handled by its own dedicated function. Make sure the target transform is placed above the player's head. This gives the camera a clean point to follow. Now you can move the camera with the mouse, and you'll see it smoothly rotate around the player based on your input. Now we are adding a group of variables that will help us improve the behavior of our camera. The first set is related to collision. When the camera moves behind the player, it might pass through walls or objects in the environment. The variable isClipped will tell us whether the camera is currently being pushed forward because something is blocking it. Desired position will store the ideal position of the camera before checking for collisions. Min distance and max distance define how close or how far the camera is allowed to move from the player when avoiding obstacles. These values help us keep the camera at a comfortable distance while still preventing it from going inside walls. Finally, collision mask lets us choose which layers the camera should detect. This way, we can decide what counts as an obstacle and what should be ignored. The next group of variables is for clamping the camera rotation. Use pitch clamp allows us to enable or disable limits on the vertical rotation. When it is active, min pitch and max pitch define how far up or down the camera can look. This prevents the camera from flipping over the player or rotating in unnatural ways. In the same way, use yaw clamp controls whether we want to limit the horizontal rotation. If it is enabled, min yaw and max yaw define the allowed range. This can be useful in games where the camera should not rotate freely around the character. All these variables give us fine control over how the camera behaves, and they will make the system feel much more polished and reliable once we implement the logic behind them. Now we move this part of the code into its own function called Calculate Camera Position. This keeps our camera logic cleaner and makes each step easier to understand and maintain. This function is responsible for limiting how far the camera can rotate. We start by checking whether pitch clamping is enabled. If it is, we use math clamp to keep the pitch value inside a safe range. This prevents the camera from looking too far up or too far down, which could create strange or uncomfortable angles during gameplay. We do the same for the yaw value. When yaw clamping is active, the camera can only rotate within the horizontal limits we defined earlier. By keeping these limits optional, we can decide whether the camera should have full freedom of movement or stay within a controlled range, depending on the style of game we want to create. This function handles one of the most important parts of a third-person camera, preventing the camera from going through walls or objects in the environment. We start by calculating a direction vector. This direction goes from the player toward the camera's desired position. We normalize it so that it only represents direction, not distance. Then we measure how far the camera wants to be from the player. This gives us the maximum distance we should check for obstacles. Now comes the key part. We use a sphere cast. A sphere cast is similar to a raycast, but instead of a single line, it uses a small sphere. This helps us detect collisions more reliably, especially when the camera is close to corners or uneven surfaces. If the sphere cast hits something, it means there is an obstacle between the player and the camera. In that case, we calculate a new distance that places the camera just in front of the obstacle. We subtract a small amount to avoid placing the camera exactly on the surface, which could cause jittering. We also clamp this distance so the camera never gets too close or too far from the player. This keeps the camera behavior consistent and prevents extreme movements. After calculating the corrected distance, we update the desired position, so the camera moves to this safe spot. We also set the isClipped flag to true, which can be useful if we want to add visual feedback or adjust camera behavior when clipping happens. If the sphere cast does not hit anything, it means the camera has a clear line of sight to the player. In that case, we simply mark isClipped as false and keep the original desired position. This entire function ensures that the camera always stays outside of walls and objects, giving the player a smooth and professional third-person experience. Now, we update the Move Camera function so it checks the isClipped flag. If the camera is clipped, we snap directly to the corrected position. Otherwise, we keep using smooth movement. We place the lookat logic inside its own function called lookatCamera. This keeps the script organized and makes the camera rotation step clear and easy to manage. Now we go back to late update and call all the functions we created. First, we read the input, then apply the clamps, calculate the camera position, run the anti-clipping check, move the camera, and finally make it look at the player. This gives us a clear step-by-step flow for the entire camera system. Now, remove the vector tree type and keep only desired position, since we already declared it earlier. If this video helped you, consider subscribing and leaving a like. It really supports the channel. Thanks for watching, and I hope to see you in the next tutorial.